So back to section 11.1, sequences continued. We had left off in the last lecture video talking about how to explicitly write a sequence of terms as its formula, as its explicit formula. So I want to just start off again with a couple more examples doing that, and then we'll get into talking about looking at the behavior of what happens to these sequences as n goes to infinity. So if we were looking at this sequence, and again, I'm going to go ahead and use a table to express it. Some of these you probably don't need to use a table, but I find it helpful. So if I just start off by listing, and again, sequences, unless otherwise indicated, we tend to start our sequences at 1. I'm going to give myself a little more space. 1, 2, 3, 4, and so on. And we're trying to come up with how would we express, if this was the sequence, how would we express the nth term as indicated by its index, as determined by its index. So 1, let's see, we've got 1, 1/2, 1/3, and I think this one is pretty obvious. By the time we get to the nth term, the a sub nth definition would be 1 over n. So we would express that. We could say a sub n equals 1 over n is one way to express it. The assumption here is that we assume the index starts at 1, that the index starts at 1 and increases. We don't have to write that. That's just the assumption. The other way we could write a sequence is we could put it in notation like this with the indication that n equals 1. Again, we don't normally write it. I guess I can put it in a slightly different color. We don't normally write it, but also the indication is that we're looking at an infinite sequence. If there's nothing given on this upper portion here in terms of the index, then it's indicated that we're going to continue on towards infinity. Okay, so let's keep going. We'll keep looking at a couple more of these. So on this one, if we were to want to write this in its explicit definition, 1, 2, again, we'll just start at 1. We can always adjust, and in one of the examples before I talked slightly about adjusting the index, and we can do that if we want to. We can play around with adjusted indexes, but for now we'll just assume that we want to start at n equals 1 and write a pattern. Come up with what is the pattern? What's the explicit definition for these sequences? So I'm going to go that far. I think we can see it after just the first 4 terms. If you need more terms, there are more terms given there. But now we're kind of looking at it and we're saying, oh, look at that. The sign switches, which we can use a switch. So as I had defined in the first video, the switch is -1 to n, or n minus 1, or n plus 1. So we'll play with that a little bit. I would say on this one, it's looking like each time we're going up by 2. So we've got a 2 times 1 here. On this next one, we have that -1 times, there's a 2 times 2. On the third term, we've got a 2 times 3. And on the fourth term, we have a -1 times 2 times 4. And so we can see here that index popping up. So by the time we get to the nth term, the nth term is going to have it's going to have a switch on it, so it's going to have a -1. Since at the first term, when n equals 1, which is odd, we had a positive, we're going to want to put a n plus 1 here, or an n minus 1. Either of those actually work, and so sometimes there's multiple ways that you could express the same explicit formula. So we could write this as -1 to the n plus 1 or n minus 1. Either of those works here. And then we have a multiplication by 2n. And that's what gives us the explicit formula here. So -1 to the n minus 1 times 2n. And you can always double check, just plug in n equals 1 and see if we're going to get the correct sequence here. So if we plug in n equals 1, -1 to the 0 would be positive. And if we had put n plus 1 here, 1 plus 1 would be 2. So -1 to the second power, of course, would be positive as well. So just note here, could have used n plus 1. Technically, you could have used n plus, or, well, you wouldn't want to go back into the negatives. That's just not normal form with sequences, but you could have gone even n plus 3 or n plus any odd number if you wanted to. You can really play around, I guess, with that switch. So you could have used that, and then times 2n. All right, and again, the assumption here, I won't write it, the assumption here is that we're starting at n equals 1 unless otherwise indicated. All right, let's just do one more. This guy's got a switch on it too. And let's just run through this pretty quickly, a little warm up into sequences again. So n, if we go ahead and start at 1, 2, 3, 4, coming up with what is going to be the explicit formula for the nth term. So if we've got -1/4, positive 2/9, -3/16, positive 4/25, and we want to come up with that nth term here. So again, I would say, as I mentioned, you can see pretty obviously you've got a switch here. So in this first one, you have -1 over, and then I see those perfect squares. So I'm just going to express that as 2 squared. Then I've got a positive for the second term, so 2 over 3 squared. And for the third term, I have a -1 times 3 over 4 squared. And then I've got a positive, I have a positive 4 over 5 squared on this one. And you could write that 4, I guess, as 2 squared, but I'm looking ahead, or looking backwards actually at the pattern, and you can see in the numerator you're gonna have a switch, -1 to a power. You also have the actual index, n, appearing in the numerator, and then in the denominator you have perfect squares. They are 1 larger than the index, and so the way we could indicate that is with an n plus 1. So we've got a switch. So for the nth term, we have a switch. This one, we have the nth term, the first term actually starts as a negative. So at n equals 1, we want this to be negative. So we would put n on that. And then we're going to have, in the numerator, we're also going to have n. And in the denominator, we're going to have n plus 1 squared, because the denominator is increasing at, or the denominator is a perfect square, but it is 1 larger than the index at each term. And there we go. So there we have our a sub n is equal to -1 to the nth, n over the quantity n plus 1 squared. And that's how we can express our nth term. Okay. So not every sequence can be actually expressed explicitly, as we've been doing. So some sequences we actually can't express in an explicit form. And some of these sequences you've probably seen before. For instance, the Fibonacci sequence. This is one that we actually define recursively in terms of the previous terms. So the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21. Each term is determined by the sum of the 2 preceding terms. So in math notation, what we do is we write that as this sequence where we say for f sub n, for n equal 3 to infinity, and then we have to define how f sub n is defined. And we have to start off with, since it starts at the index equals 3, we define f1 and f2. You have to start by, when you're defined recursively, you have to start with the first couple terms. So f1 is 1, f2 is 1, and then the nth term is the sum of the previous 2. So f sub n minus 1 plus f sub n minus 2. So that's one way to do it. That's called a recursive definition of a sequence. And then another way we could define sequences is for something of this form. And of course, this guy, if a sub n is the nth decimal place in the number pi, well, that's never going to have a pattern. That can never be defined as an explicit sequence. So in this case, 3.14159 ... It goes on and on and on forever. And so this sequence would be 1, 4, 1, 5, 9, no pattern. We would just write it that way. And another one would be if we use some real world data. We wanted to say the sequence of numbers that we want to look at is, say, the average temperature on the first day of January in Nevada City. And then you would also have a sequence that doesn't have an explicit definition, but is still a sequence, a list of numbers. Okay. So now that we've talked about just what are the general ideas of infinite sequences and what what we can do to write them explicitly so we can look at these. Let's talk about graphing these. So if we were to want to actually graph a sequence, what we're going to do is we're going to consider the nth term essentially as a function of n. And so what we end up with is we end up with a list, or we could think of it actually as a table of numbers, like the table that we had. Actually, it's the exact table that we were looking at when we were trying to come up with the explicit definition. And we look at a table where these become ordered pairs that we're actually graphing. So 1, a sub 1, 2, a sub 2, and we graph these as our x and our y coordinates into the coordinate plane. So here's just a quick little graph, a little visual here. And I'm going to show you something from Desmos here in a minute. But if this was the sequence, so the sequence that I have right here is 1 over 2n. So the first term is 1/2, and the second term would be 1/4. And so if we were to actually be graphing the second term, that would be right here, and then 1/8, and we would just keep going, and we would be graphing a set of dots in the coordinate plane. So that's just the general idea of graphing sequences, and I just wanted to show you, you can graph them by hand. It ends up being just a set of dots, an infinite set of dots when we graph these, but you can also use technology to graph these, and you can see the visual. Since we are actually graphing infinite sequences, it's kind of nice, you can see the visual come about quickly. So I grabbed one sequence, 1 over n, and I just went into Desmos and embedded it here so that we could actually take a look. So here's the sequence, a sub n equals 1 over n. We're going to talk about this idea of converging and so forth here in just a second, but just so that you could get the visual, if I actually just start this is going to indicate we're going to see the dots. It's an animation. We'll see the dots increasing, and I will close this, and you can see what's happening here. Now they're going backwards. But you can actually see all of those ordered pairs being plotted out to n equals 100. And they are just a set of dots, and we're actually plotting 100 points right here in Desmos. It's just a set of dots that we're looking at, but we're going to think about all the things that we did back in Calc 1 with limits and think about, well, does this have a limit? Does this sequence actually approach a value as we head out towards infinity? And that's where we're headed in this section, and here's a nice visual of something that occurs like that. All right, so let's look at another one. So what if we had this sequence? What if we looked at a sequence that actually had a switch on it, -1 to the n, -1 to the n, n times, -1 to the n times n over n squared plus 1. So for this sequence, a sub n equals -1 to the -1 to the nth times n over n squared plus 1, I just went into Desmos and changed, I just adjusted the actual definition of the sequence here, and we can graph this and see what happens when we have a switch. So I'm going to scroll up here a little bit and go ahead and get the animation started. So if I hit play right here, it's going to go pretty quickly, and it almost looks like we have two sequences, but that's because the terms are flipping from positive to negative. So if I go out, let's go out to 15 right here, and I'll go ahead and label these. And that might be too many to visualize. Well, we can zoom in on that a little bit. So if we zoom in on that, what you can see is happening here is every other term, because the even terms are positive, but the odd terms are negative. Now the size, the magnitude of the terms is decreasing. They're getting smaller, smaller, smaller if you look at the y values here, but they are flip-flopping back and forth. They are what's called oscillating back and forth across the x-axis here. Now, I'm going to go ahead and get rid of the labels. It makes it very busy. And let's go ahead and zoom back out again here so we can see what happens, at least as we go towards 100. And, oh shoot, a little bit too far. There we go. I scrolled off of it. And we can see that that is oscillating. We're back and forth, back and forth, back and forth. But you can see from this graph, even though we are going between positive and negative terms, kind of bouncing back and forth across the x-axis, the actual sequence itself is still approaching zero. So that's kind of some interesting behavior. Oscillation doesn't always approach a value, but sometimes we do oscillate back and forth and approach a single value. And this idea of approaching a single value brings us to our next piece. And so the next piece that we want to talk about here is what is a limit of a sequence. So now that we've talked about sequences and graphing sequences, how do we actually define the limit of a sequence? How do we define the limit of a list of numbers, which is what a sequence is? And so what we're going to do is we're going to consider what happens to those terms as the index, as n approaches infinity. And this is very, very similar, and we're going to use a lot of the same approaches that we did when we took limits of functions. So we'll get through all of that, get through some definitions here in terms of limits, and then we'll get into actually evaluating these. So we say that a sequence converges if to a limit L if that limit exists. So let's highlight that. So this idea of convergence. So a sequence is said to converge to a limit if the limit as n approaches infinity of a sub n of the terms exists. What that means is if the terms in the sequence approach a finite value. If it does not converge, then we say that it is divergent. So if it does not approach this value, if we do not approach a finite value L as we go towards infinity in the index, then we say that the sequence is divergent. So I plotted that 1 over n above. So if we look back at this graphical example, and actually it's still being animated here. If we look back at that graphical example, this was the sequence 1 over n. And what we can see is happening here is that we are definitely approaching a limit, and the limit that we're approaching here is 0. Okay? So it seems as though the limit is 0 for this particular case. We are approaching 0. The terms a sub n appears to be approaching 0 as n approaches infinity on this example from the graph. So we can see that as we head out towards infinity, we actually only have, that graph only goes to n equals 100, but we're actually letting it approach infinity, and that pattern is not going to change. So what we can say here is that the actual distance, getting back into our official definition of limits with epsilons and so forth, the distance from the terms to 0 can be made as small as we want, as long as we go out far enough with the index, as long as we go out far enough with n. So the limit of a sequence, what we're going to do here is we're considering, here's the official definition. What we're doing is we're considering what happens to a sub n as n approaches infinity. We say that it converges if given any epsilon greater than 0. So we can pick any number we want. We can make it as small as we want. Then there must exist a positive integer n. So there must exist some positive integer n, so that a sub n minus L in absolute value, and what this is, this a sub n minus L, that is actually referring to the distance of a sub n, the terms to the limit L. It can be, essentially, it can be made as small as we want. That's what our definition of the limit is, that actual distance, meaning the terms get so close to their limit because we can make them as small as we want, as long as we let n, the index, be greater than or equal to this integer n. So that's just a way of saying that the limit as n approaches infinity of a sub n equals L. Okay, and so there's just a couple different ways. Otherwise, if that cannot be shown, if we can't show that, then we would say that the sequence is divergent. So that's basically, if we go all the way back into how we defined limits back in Calc 1, thinking of an epsilon neighborhood around a function as it approaches a limit. That's what we're doing right here too. So if we actually think about creating an epsilon neighborhood for our sequences. So here's a couple of little graphs of sequences approaching limits. And what we're saying is that if we had some little epsilon neighborhood, if we zoom in on this, if we have some little epsilon neighborhood, so this would be L, so if we had some little epsilon neighborhood here, L minus epsilon and L plus epsilon, I'm just trying to get that definition on the recording here too. So up here at that definition, that absolute value, if we break that out, what we're saying is that if we were to create an epsilon neighborhood. Here's my epsilon neighborhood. Given any epsilon, if I create an epsilon neighborhood around the limit, then there has to exist somewhere in it. For this particular graphical example, it looks like it's occurring right here. So for all of the n's bigger than this capital N, my terms are within that epsilon neighborhood. So my terms are all within that little epsilon neighborhood. And we could do the same sort of thing over here and just say, let's make some epsilon neighborhood. Oh, that was not a very straight line. An epsilon neighborhood here. And we can make this, I mean, I have to, for purposes of the picture here, I have to create a little bit of distance here so you guys can see it. But remember, this epsilon neighborhood can get as small, epsilon can be as small as we want it to. That's the definition. And so this is saying basically it looks like this occurs right here. My capital N occurs right here. And then for every n, every little n after that, my terms are within that epsilon neighborhood. So that is showing right there the actual official definition of the limit of a sequence. Okay. All right, so just one little summary, and then we're going to have to stop this video for now. But this is what we're saying. So for convergent sequences, you can show that given any epsilon greater than 0, you can find capital N, so that for all of the terms, little n greater than that capital N, that the distance of a sub n to L, and that's how we express distance in mathematical form. The absolute value of a sub n minus L is less than epsilon. Okay. Now, for diverging sequences, sequences will either grow or decrease without bound or oscillate without ever reaching a limiting value. And so, for instance, let's just start at this one. What we have here is the sequence where it just switches between -1, +1, -1, +1. And if you actually think about what that would look like if we were to try to graph that and find an epsilon neighborhood, what you'll see is, make this +1, 1, 2, so forth. So if we start at -1, so we would be plotting points that look like this. And this sequence is diverging. It is never going to, it's just oscillating back, forth between -1 and +1. And this guy is going to have to diverge. It's never going to come within an epsilon neighborhood of a single value because it's flip-flopping between positives and -1s. So this guy diverges. So those are just two of the very first examples of talking about convergence and divergence of two sequences. So 1 over n, it will actually converge, and we can show that it converges to 0. Now the sequence -1, 1, -1, 1, -1, 1 actually diverges. It's just going back and forth, and never coming to a finite value. Okay, we will come back and start talking about our connection to limits of actual functions, thinking about how do we connect the dots, essentially. And if we were to try to connect the dots here, you can see that we have an oscillating function. And so how do we connect the dots, thinking about functions and connecting all of our function theory on limits to our newer sequence theory? So we will come back and put that into another video.